Imagine a material that is several times stronger than steel, but significantly lighter than aluminum. A material used in aircraft structures, spacecraft, racing cars, wind turbine blades, and high-performance sports equipment. This material is known as carbon fiber, and it has become one of the most important advanced materials in modern engineering. At first glance, carbon fiber may look simple. It often appears as a black woven fabric or a bundle of very thin threads. In reality, its internal structure is extremely sophisticated, and its production process is one of the most technologically demanding in materials engineering. Each individual carbon fiber filament is made of millions of carbon atoms arranged in a highly ordered crystal structure. These atoms form long, layered chains that run along the length of the fiber. Because of this orientation, the fiber can withstand enormous tensile forces without breaking. Interestingly, carbon fiber does not start as pure carbon. The production process actually begins with a completely different material, a synthetic polymer fiber. If you like similar educational content, please like, subscribe, and share the video with your friends. The most common precursor material is a polymer called polyacrylonitrile, usually abbreviated as PAN. Today, roughly 90% of the carbon fibers produced worldwide are made from PAN-based precursor fibers. The process begins with the production of these polymer fibers. The raw polymer is melted and forced through extremely small nozzles in a process known as spinning. As the material passes through these tiny openings, it forms very thin filaments. Each individual filament typically has a diameter of only 5 to 10 micrometers. To understand how small that is, a human hair is roughly 10 times thicker. Thousands of these filaments are then gathered together into bundles known as tows. A single tow can contain several thousand individual filaments, and in some industrial fibers even tens of thousands. Once the precursor fibers have been formed, they must undergo the first important stage of transformation called stabilization. During stabilization, the fibers are heated to temperatures between about 200 and 300 degrees Celsius while exposed to oxygen. This heating causes chemical reactions within the polymer structure. The long polymer chains begin to reorganize and form more stable molecular structures. This step is crucial because it prepares the fibers for the extremely high temperatures that will follow in the next stage of production. During stabilization, the fibers also gradually change color. They become darker as the chemical structure of the material begins to transform. However, the material is still not carbon fiber yet. To turn the polymer into real carbon fiber, almost all elements other than carbon must be removed from the structure. This transformation takes place during the next stage known as carbonization. After the stabilization stage, the precursor fibers are ready for the most important transformation in the entire production process. This stage is called carbonization, and it is here that the polymer material begins to turn into real carbon fiber. The stabilized fibers are fed into long industrial furnaces. These furnaces can extend for dozens of meters and are divided into multiple temperature zones. Unlike the stabilization stage, this process takes place without oxygen. If oxygen were present, the fibers would simply burn. Instead, the furnaces are filled with an inert gas atmosphere, usually nitrogen. As the fibers move slowly through the furnace, they are heated to temperatures between 1,000 and 1,500 degrees Celsius. Under these extreme conditions, the internal chemical structure of the polymer begins to break down. Atoms of elements other than carbon are gradually removed from the material. Hydrogen, oxygen, and nitrogen atoms are released from the structure and escape in the form of gases, such as hydrogen, ammonia, and various hydrocarbons. As these atoms leave, the remaining structure becomes increasingly rich in carbon. At the same time, the internal atomic arrangement of the material begins to reorganize. The original polymer chains gradually transform into layers of carbon atoms that resemble the crystal structure of graphite. Graphite is a form of carbon in which atoms are arranged in thin, flat layers. These layers are extremely strong within their plane. In carbon fiber, these layers become aligned along the length of the fiber. This alignment is what gives the material its extraordinary strength and stiffness. In many cases, the process continues with an additional stage known as high-temperature carbonization or graphitization. During this stage, the fibers may be heated to temperatures between 2,000 and 3,000 degrees Celsius. At such extreme temperatures, the carbon structure becomes even more ordered. The layers of carbon atoms align more precisely, increasing the stiffness and mechanical performance of the fibers. One remarkable aspect of this process is that the fibers maintain their shape even under these extreme temperatures. Diameter of the filament remains extremely small, typically around 5 to 7 micrometers. After carbonization, the resulting fibers consist of more than 90 to 95% carbon. This near-pure carbon structure gives the material its exceptional properties: very high tensile strength, extremely high stiffness, and very low weight. However, even at this stage, the fibers are not yet ready for industrial use. The surface of the fibers is relatively smooth and chemically inactive. If these fibers were used directly in composite materials, resins would not bond effectively to them. For this reason, the fibers must undergo another important step: surface treatment and coating, which prepares them for use in advanced composite materials. After carbonization, the fibers have already developed their remarkable mechanical properties. They are extremely strong, very stiff, and incredibly lightweight. However, at this stage, they are still not ready to be used in real engineering applications. The reason lies in the surface of the fibers. Freshly carbonized fibers have a relatively smooth and chemically inactive surface. This means that if they were directly combined with polymer resins, the bonding between the fiber and the resin would be weak. In composite materials, strong bonding between these two components is essential for transferring mechanical loads effectively. To solve this problem, carbon fibers undergo a process known as surface treatment. During surface treatment, the fiber surface is slightly modified in order to improve its chemical reactivity and roughness. This is usually done through controlled oxidation processes. The fibers may pass through chemical baths or undergo electrochemical treatment. These processes create microscopic irregularities and introduce chemical groups on the surface of the fibers. Although these changes occur on a very small scale, they have a huge impact on the performance of the final material. The modified surface allows resins to adhere much more strongly to the fiber, creating a durable bond between the two materials. After surface treatment, the fibers receive a thin protective coating known as sizing. Sizing is typically a very thin polymer layer applied to the fibers. This coating serves several important purposes. First, it protects the delicate filaments from mechanical damage during handling, winding, and further processing. Even though carbon fibers are extremely strong when stretched, individual filaments can be damaged by friction if left unprotected. Second, the sizing layer improves compatibility between the carbon fiber and specific types of resin systems used in composite materials. Once the fibers have been treated and coated, they are wound onto large spools. Each spool may contain several kilometers of continuous fiber. The fibers are then processed into different forms depending on their final application. One common form is carbon fiber fabric. The fiber bundles are woven together in patterns similar to textile fabrics. These woven sheets are lightweight yet extremely strong. Another form is unidirectional carbon fiber, where the fibers are aligned in a single direction. This type of structure is used when maximum strength is needed along a specific axis. These fabrics or fiber sheets are then combined with polymer resins, such as epoxy resins. When the resin cures and hardens, it forms a carbon fiber composite. In these composites, the carbon fibers carry most of the mechanical load, while the resin holds the fibers together, distributes stress between them, and protects the structure. The result is a material with an exceptional strength-to-weight ratio. Because of these properties, carbon fiber composites are widely used in advanced engineering fields. They appear in aircraft fuselages, spacecraft components, racing car chassis, wind turbine blades, and high-performance sports equipment. For example, modern passenger aircraft may use carbon fiber composites for large portions of their wings and fuselage structures. Despite these advantages, carbon fiber is still relatively expensive to produce. Although carbon fiber offers extraordinary mechanical properties, it remains a relatively expensive material. The main reason lies in the complexity and energy intensity of the manufacturing process. The production of carbon fiber requires multiple stages that must be carefully controlled. Each stage, from polymer spinning to stabilization, carbonization, and surface treatment, must be performed under very specific conditions. Even small deviations in temperature, tension, or processing speed can affect the final quality of the fibers. One of the most time-consuming steps is stabilization. During this phase, precursor fibers must move slowly through long furnaces while undergoing chemical transformations. If the fibers are heated too quickly, their internal structure can become uneven or damaged. After stabilization comes carbonization, which requires extremely high temperatures. Industrial carbonization furnaces operate at temperatures above 1,000 degrees Celsius, and in some cases much higher. Maintaining such temperatures continuously requires enormous amounts of energy. Additionally, the process must take place in an oxygen-free environment, usually filled with inert gases such as nitrogen. This adds further technical complexity to the manufacturing system. Another factor contributing to cost is precision control. Carbon fibers are extremely thin, only a few micrometers in diameter, and must maintain a nearly perfect structure along their entire length. Even microscopic defects can reduce strength significantly. For this reason, modern production lines include advanced monitoring systems that constantly track fiber tension, furnace temperatures, and material quality throughout the entire process. The precursor material itself also plays an important role in the final cost. The most common precursor, polyacrylonitrile, must be produced with high chemical purity and consistent molecular structure. Any variation in the precursor material can influence the performance of the finished carbon fiber. Despite these challenges, carbon fiber has become one of the most important materials in advanced engineering. In the aerospace industry, carbon fiber composites allow aircraft structures to be significantly lighter. Lower weight reduces fuel consumption, increases range, and lowers emissions. In motorsport, carbon fiber structures provide extremely high strength while minimizing weight. Modern Formula One cars use carbon fiber monocoque chassis that protect drivers even during severe crashes. Carbon fiber is also essential in renewable energy, especially in large wind turbines. Modern turbine blades can exceed 100 meters in length, and the material must be both lightweight and extremely strong to withstand aerodynamic forces. Researchers are now working to make carbon fiber more affordable and accessible. One promising direction involves developing alternative precursor materials, such as lignin derived from biomass. Lignin is abundant in plant material and could potentially reduce the cost of carbon fiber production.